Hello and welcome to problem 19 in my Calculus 3 or multivariable calculus problem solving series. In this video, we're going to look at how to solve triple integrals using spherical coordinates. So in the previous video, we learned about cylindrical coordinates and how to use them to solve triple integrals. But in this video, we're going to be looking at spherical coordinates. So these coordinates, as they're named, take the shape of a sphere. And instead of having x, y, and z, we have rho, phi, and theta, where rho is like the radius of your sphere, phi is the angle downward from the z-axis to the y-axis, and theta is like in the cylindrical coordinates, it's the angle from the x-axis to the y-axis. So using rho, phi, and theta, we can get any point in 3D space. But we also have to limit them so that rho has to be greater than or equal to 0. Theta has to be between 0 and 2 pi. So this means that the maximum is 1 revolution. And phi has to be between 0 and pi. So phi can be from to the positive z-axis all the way to the negative z-axis. And to convert between normal coordinates and spherical coordinates, you can use this, which says that x equals p sine of phi times cosine of theta. Y is p sine of phi times sine of theta. And z is p cosine of phi. So when we take the triple integral using spherical coordinates, our small element of volume will be equal to p squared times sine of phi times d rho times d phi d theta. And this diagram shows how that. So a small piece of the volume, one side is d rho, while this side is rho times sine of phi d phi, and finally the third side is rho d theta. And when you multiply all these, you get your small element of volume. So let's go ahead and look at an example about how to use spherical coordinates to solve triple integrals. So we want to find the triple integral of f of x comma y comma z, which is 16z, over the volume x squared plus y squared plus z squared equals 1. So this sphere, but only the top half of the sphere. And now we have to define our bounds for our triple integral. So our bounds on rho are going to be from 0 to 1, because this sphere has a radius of 1. Our bounds on phi are going to be from 0 to pi over 2. This because the angle from the top of the z-axis to the bottom of the sphere is 90 degrees, or pi over 2. The bounds on theta are going to be from 0 to 2 pi, because this gives us one complete revolution around the sphere, or semisphere. So now we can set up the triple integral, and it's going to be like this. So we have the integral from 0 to pi over 2 for phi, the integral from 0 to 2 pi for theta, and the integral from 0 to 1 for rho. And dv is this portion, and notice that we have rho squared times sine of phi, and this is the element of volume as we saw before. And our function is here, 16p cosine of phi, because we converted it from the normal coordinates to spherical. And then we solve this triple integral like we did in the previous videos, and we see that this equals 8 rho cubed times sine of 2 phi, and then we take the integral with respect to rho, and we see that we get 2 sine of 2 phi. Then we take the integral with respect to theta, and we're just going to multiply by 2 pi. So we get 4 pi times sine of 2 phi. Finally we take the integral with respect to phi, and we get minus 2 pi times cosine of 2 phi, and we evaluate it from 0 to pi over 2, and we find that it equals 4 pi. And so what this answer represents is the mass of that region or volume that we integrated of.